All right, my chemistry students, moving right along, we're now going to get into the equilibrium expression, and we're going to look at it in several different forms. Some of this should be familiar, and some of this should be new. So going back to our simple equilibrium between an A and a B, and making sure I've got my right place here. Yes, so we remember now the free energy of the reaction is equal to the sum of the stoichiometric coefficient times the chemical potential, where remember I can write the chemical potential of J as the following: plus RT natural log, and we noted that that was PJ over P naught, so I'm now going to replace that quantity with the activity of J. Right? So let's just write that again so we make sure that that's clear. Okay, plus RT natural log activity of J. So now when we put that in this sum to compute the free energy of the reaction, including times its stoichiometric coefficient, we come up with the following. So I've got a sum here that will sum over all chemical species J. And now I'll just write that as nu J times this whole quantity, nu J standard, plus RT natural log of the activity. And now distributing this through, we've got to do some algebra here. So that's going to become the sum of nu J times mu J standard, and I'll leave that alone. I'll factor out an RT because that is the same for any chemical species. So that's RT sum over all chemical species J. And now that becomes nu J times natural log of the activities. So we should recognize right away that this quantity right here is just going to give us the standard free energy of the reaction. So this is going very similarly to how we derived this before. But now, because we put this placeholder for activity, we're no longer beholden to this simple reaction of A going to B. We can start thinking of it in terms of real concentrations, whether it be solvent activity, solute activity, etc. Okay? So now I'm going to keep going with this and write RT sum of J, but now if you recall in this natural log property, when I have a quantity times a natural log, I can also write that as a power. So that's natural log of AJ raised to the nu J. Okay? And then now something algebraically interesting happens. So I'll just write this generically. So if I have the sum of the natural log of X, so that is the same thing as saying the natural log of the product of X. So you might not be familiar with this big capital pi. That means product. So sigma is sum, so add them all up. Big capital pi is product, meaning multiply all of them. So now rewriting this expression right here, that's going to go delta G of Rxn equals delta G standard plus RT. And now that becomes the natural log of the product of the activities raised to their stoichiometric coefficient. And if you recall from last time, we called everything that was inside this natural log the reaction quotient Q. So now we have a way of getting an equilibrium expression based on activities for any number of reactions that might not just be this simple A goes to B in the ideal gas approximation. So here we now have that expression. So the reaction quotient are the product of the activities raised to their stoichiometric coefficient, where those activities are their initial values for the reaction quotient, and we replace Q with K when those activities are related to equilibrium. So let's do an example to see how this all plays out. So we remember that nu of A is going to be -2, nu of B is going to be -3, nu of C is going to be +1, and nu of D is going to be +2. So now writing the equilibrium expression for this, I'm going to just list them all as products. So now that becomes A, and I'll replace the J with its chemical identity. So that's A of A, and it's got to be raised to its stoichiometric coefficient power. Okay. So then now, right, it's a product, so we just keep multiplying them. That's A of B raised to its stoichiometric coefficient power. And now that's times the activity of C, and it's raised to +1, so I'll just leave it like that. And now that's times the activity of D squared. So doing just some simplification on that, this now becomes the activity of C times the activity of D all squared divided by the activity of A all squared divided by the activity of B all cubed. And if you're looking at this and thinking, that's exactly how I would have written this based on what I learned in general chemistry or quantitative analysis, then you're exactly right. That's where our law of mass action comes from. But it's important to note, right, that the equilibrium expression is technically based on activities, not concentrations. So what you're routine to seeing, and I'll write this as an approximation, is that would be the concentration of C times the concentration of D squared times the concentration of A squared times the concentration of B cubed, right? You're used to seeing it like that. That is technically only approximate. It's more correct to list it in terms of their activities. Now you also might asking, what about solids and liquids? Okay, so because hopefully you remember from your general chemistry days that we don't include pure solids or liquids in the equilibrium expression. And that's because the activity of a pure liquid or the activity of a pure solid equals 1, right? Any pure phase has an activity of 1. So when we see that we just automatically drop out a pure solid or pure liquid from the equilibrium expression, it's not that we haven't dropped it out, it's just that its activity is 1, so it drops out mathematically, okay? So that's why we only include the gas phase or the aqueous phase, because those activities are not equal to 1. All right, so what about in terms of other units like pressure, okay? Well, so I've got the activity expression written there in terms of activity. What did I say? I got the equilibrium expression written in terms of activity. To be more correct, we can actually write it in terms of concentration by dividing it by that standard concentration value, 1 mole per liter. That allows us to recognize then that equilibrium expressions are unitless. And we typically call that Kc, K with respect to concentration. Well, what if I have things in terms of pressure, all right? So let's flush that out. So let's write K equals product pi of species J, A of J raised to the new J. And if we recast that in terms of the partial pressures, we get the following. So remember, the activity is just the partial pressure over some standard reference value raised to the new J power. And if we use the ideal gas law to calculate that pressure, we can plug that in. So that's going to be now product of any chemical species J. And now, if you recall, right, PV equals nRT, or P equals nRT over V, where N over V is concentration. So now I can replace that P of J with the following. That's going to be bracket of J times RT, and that's still divided by the standard pressure to keep everything unitless. And those are all raised to the new J power. So now doing some algebra here, let's keep going with that. So I'm going to separate the concentration term and write that as J raised to the new J power. And now that's times the product of the other quantities. So that's RT over P naught raised to the new J power. And so hopefully what you recognize is all of those will be a constant, with the exception of it being raised to their stoichiometric coefficient. So now continuing along with this thing, to make this equal to Kc, I'm going to divide that by standard concentration. Okay, so that will be divided by standard concentration, again, to get rid of the units. But because I divided that one by standard concentration, I've got to multiply that one by standard concentration, right? If I divide something on one half of the equation, I got to multiply it by the other half, all right? So now that's that same reference value, 1 mole per liter, times RT, divided by P standard, and now that's all raised to the new J power. Well, effectively, now what we have, I'm going to now recast this and write this as Kp based on pressures. And we can see all of that is equal to Kc. And now when I consider that all of these are constants, and when I take a product of exponents, it becomes a sum in the exponential. Now I just get this simple ratio of constants, which goes as the following, okay? And now that's raised to the delta nu J power, where delta nu J is just the sum of the coefficient of the products minus the sum of the coefficient of the reactants. And maybe you remember this equation from Chem 109, right? If we've got an equilibrium expression in terms of moles per liter, we can recast that into its correct expression in terms of partial pressures with this conversion factor. So it's important to note that Kp, Kc, and just K based on activities are not equal to each other. Kc and K based on activities are close. Let's write that down. Okay, those are very close to each other, but those are not the same as Kp. The values are different unless, of course, the stoichiometric coefficient turns out to be 0, right? If the sum of the coefficients is 0, then that whole thing drops out, and then Kp does equal Kc. Okay, we're going to explore this in the Igor 4 assignment, which you will be working on before you probably see this video. So we'll catch up on this in due time. I'll see you in the next video.